Given that z is 1 minus 2i, verify that z to the power of 5 conjugate is equal to z conjugate to the power of 5. So to verify this, we're going to check each of these and we're going to show that they give the same answer. So starting with that one first, binomial expansion, Pascal's row, 1, 5, 10, 10, 5, 1. First thing, decreasing powers, 1 to the power of 5, 1, 1 to the power of 4 is 1. All of these are going to be 1 because it's always 1 to the power of something. And then increasing powers of minus 2i, so minus 2i to the 0 is 1. Minus 2i to the power of 1 is minus 2i. Minus 2i all squared is going to be 4i squared. But I squared is equal to minus 1, so that's going to be minus 4. Minus 2i all cubed will be minus 8i cubed. I cubed is equal to negative 1, so this just becomes, negative I, so it becomes 8i. Minus 2i all to the power of 4 is going to be 16i to the 4. But I to the power of 4 is equal to 1, so that disappears. And minus 2i to the power of 5 is minus 32i to the power of 5. But I to the power of 5 is just the same as I. And so multiplying down, we get that z to the power of 5 is equal to 1 minus 10i minus 40 plus 80i plus 80 minus 32i, which is equal to 41 plus 38i. And so Z5 conjugate is equal to 41 minus 38i. Now looking at the other side, first of all we're going to find Z conjugate, which is 1 plus 2i. And then we're going to raise that to the power of 5. So we're going to do the same thing. 1, 5, 10, 10, 5 and 1. 1 to decreasing powers is always going to be 1. And then 2i to the power of 0 is 1. 2i to the power of 1 is 2i. 2i to the power of 2 is 4i squared. But I squared is equal to negative 1, so that's going to become negative 4. 2i to the power of 3 will be 8i cubed. I cubed is negative I, so that's going to become minus 8i. 2i to the power of 4 is 16i to the 4. But I to the power of 4 is just equal to 1. And then finally 32i to the 5, but I to the 5 is equal to I, so that just disappears. Which means that Z conjugate to the power of 5 is equal to 1 plus 10i minus 40 minus 80i plus 80 plus 32i, which is equal to 41 minus 38i. And we can see that these two things are the same, so that verifies the fact that z to the 5 conjugate is equal to z conjugate to the power of 5. Now notice what happened in there is that, well, the first two rows were exactly the same because the Pascal's triangle didn't change, it was a power of 5. And the ones didn't change because the real part was the same. What changed was in these imaginary parts, the two i's, but not every bit changed. All of the even powers of I stayed the same. Because when we square negative 2, or we square 2, we get 4, we get the same value. What happened with the odd powers, though, is that we ended up getting negatives of those at each stage. We got the negative value for each of the imaginary parts in this expansion, because this one had a negative and this one had a positive. So when we were raised to an odd power, these ones were negative and these ones were positive. We then had to deal with the powers of I, which changed some of those signs, but that happened in exactly the same way on both sides. This was I cubed for both of these ones, so it changed the sign. This was just I, so it didn't change anything. This was I to the 5, so it didn't change anything. But those ones, the signs changed because of this sign here, which is all to do with the fact that these were conjugates. The conjugate is what changed the sign. So that's why these two things are the same, and you can kind of generalize that idea to visualize why this would be true for any power and indeed any complex number z.